Well, thank you, Guido. Thank you for that lovely introduction. It's great to be here among friends. It's great to be here in Brazil. I thank you for the introduction. I thank Esper for putting this meeting together and inviting me to come. And I thank George for his hospitality as well. I do love Brazil. It's a beautiful country. It's got beautiful people. It's got beautiful beaches. And, of course, the beautiful game. Now, I want to talk to you a little bit about that. I've gotten together with my gringo friends, and we have a recommendation to you, and here's what it is. We think that you must change your football to our football, and there are many good reasons why this will be good for you. First, it will allow your gringo friends to come down here and visit you every time our team plays yours, and second, it will allow you to come to the States every time your team plays an away game with us. But here is the most important advantage. If you switch to American football, you will never, never have to play Germany again. All right, so what I'm going to talk to you about is the determinants of cardiovascular risk in HIV infection. And the thesis that I will propose to you is that this is a conspiracy between monocytes and CD8 positive T cells. We think of CD8 positive T cells primarily as cells that have cytolytic activity that protects us against viral co-pathogens. And that's probably the greatest context in which you heard of this. But I'm going to propose that in HIV disease, they actually mediate cytopathicity and disease targeted against the host. So the first slide that I have here is a slide that tells us that in the antiviral therapy era, a whole variety of soluble inflammatory markers from interleukin-6 to IP-10, which is an interferon-inducible protein, to tumor necrosis factor receptors, to soluble CD4 T, which is shed off the surface of monocytes, to D-dimers, which are products of clot fibrinolysis that indicate that clotting has been going on, all are associated with a risk of non-AIDS morbidities among patients who receive suppressive antiviral therapy. All of these patients in this study that was published in JID 2 years ago had controlled viremia, and in plasma, all these inflammatory and coagulation markers predicted morbid outcomes. Interestingly, when corrected for CD4 T cell counts, the relationship was the same, as you can see on these forest plots. The bottom figures represent the very same data when corrected for CD4 T cell counts. Even more interestingly, if we look at the same individuals, and these are 450 people followed in the ACTG, if we looked at these same markers before they started antiviral therapy, so no virologic control, no antiviral drugs, treatment naive, the very same pattern existed, and when corrected for the magnitude of viremia on the forest plots, was unaffected. So it tells us that there's a set point, an inflammatory set point, that occurs in people with untreated infection that persists even after treatment is initiated effectively with suppressive antiviral therapies, that places them at risk for morbid outcomes in the heart era. Okay, so these inflammatory mediators, I like to think of them as a soup. So there's this inflammatory soup that's linked to morbid events in treated HIV infection. And this is the common dogma. This is what we all talk about all the time. Everybody in this room knows that inflammation predicts morbid outcomes in HIV infection. But how satisfying is that understanding, really? First, what's driving these mediators? What's driving inflammation and what's driving coagulation? Second, how do inflammatory mediators cause disease? Do they really cause disease, or alternatively, are they bystanders? Which of them, if we think they mediate disease, is on the causal pathway to cause morbidity, and which are bystanders? And finally, most importantly, what are the actual mechanisms responsible for these morbid events, things like heart attacks, things like strokes, things like progressive frailty. All right, let's attack the first one first, potential drivers of inflammation and coagulation in treated HIV infection. There are numerous, and this is a slide that was modified from one given to me by Steve Deeks, and these are a bunch of the things that are plausible drivers of inflammation, activation, and coagulation. Top left, we have residual HIV production. We all know, and we had a nice presentation by Danny yesterday showing us that in people with controlled HIV, in that setting it was individuals who were elite controllers, but there's a similar, although somewhat different in magnitude, story in people receiving antiviral therapy. If you look, you can see viral expression. And in all of our patients who are well controlled on antiviral drugs, we see these periodic blips all the time. So there is virus that's produced that may be driving activation and inflammation. Second, lipids. You don't know the whole of it. You don't, not even the half of it. I don't know the half of it. The lipid perturbations in people with HIV infection, whether treated or not, are profound. And we have been measuring lipids on this naive and very primitive basis of their density. We measure cholesterol, we measure triglycerides, and then we measure high and low density and very low density lipoproteins. The fact of the matter is you can divide up the lipids, the individual lipid molecules in our plasma, into more than 1,000 different moieties. And we now have the methods that allow us to distinguish among them using these lipidomics methods. And one can see profound perturbations in the whole families of lipid subclasses, many of which are drivers or consequences of inflammation and activation. And you'll be hearing much more about that in the future. But just to summarize, perturbations in lipid metabolism, and particularly among oxidized lipids, can play an important role in driving inflammation. Third, we have co-pathogens. There are plenty of co-pathogens, and one of the most important of them that we live with is cytomegalovirus, which infects more than 95% of our co-infects more than 95% of our patients with HIV disease. And I'll present you a little data on why we think CMV is an important mediator of activation and inflammation in HIV disease. We have homeostatic responses. When people are lymphopenic or for other reasons, there are elevations in a variety of homeostatic cytokines that can drive cellular expansion, proliferation, and activation. And I'll show you some data that indicates why homeostatic responses play a role in the activation and morbidity of HIV infection. There are perturbations in normal mechanisms that we use to regulate the magnitude of inflammation and activation, and they may play a role. I won't talk much about that today. And finally, we have the concept of microbial translocation. And Dr. Arthos presented you some really nice data today about what happens very early on in the gut in persons with HIV disease. And as you know, when gut CD4 T cells are depleted by acute infection, the barrier to translocation of luminal products into the systemic circulation is attenuated, and we can find evidence of microbial products and the downstream outcomes of microbial translocation in patients with chronic HIV infection. So lots of things can drive it, and if it turns out that lots of things are driving it, the story becomes increasingly complicated. So I'm going to try to resolve all these things into a simple story and say that this inflammatory, procoagulant environment promotes cardiovascular disease in untreated infection and in treated infection. And I'm going to give you a mechanism. And the mechanism is because there's an accumulation of CD8 positive T cells and monocytes at the endovascular surface in blood vessels that results in the formation of damage to the endothelium, the lining of the blood vessels, and the formation of plaques, inflammatory plaques, and vascular pathology. That's the story. If I don't fall asleep, you can fall asleep. This is all you need to know. All right. This is a PET CT scan of the heart and aorta of a patient with who does not have HIV on the left and a patient who does have HIV on the right. And in a PET-CT scan, in this particular scan, an isotope of radiolabeled glucose is infused, and the cells that take up the glucose, meaning cells that are metabolically active, are visualized on the basis of the radioactivity that they emit. And you can see, and it's best seen on this axial view, the cross-sectional view of the aorta in an HIV-positive patient, well-controlled, is highly metabolically active. The cells that are responsible for the uptake of glucose and this radioactivity reflective of inflammation are monocytes. Let's talk a little bit about monocytes. We can divide monocytes up into several different populations, 3 different populations based upon the expression of CD16 and Fc receptor on the y-axis, and CD4 a co-receptor for lipopolysaccharide on the x-axis. This is an HIV-negative individual. Here are 3 HIV-positive individuals, and you can see that in our HIV-negative individual, most of the monocytes are CD14 high and CD16 low. Those are cells we call traditional monocytes. The distribution of those cells is different in the HIV-infected population, with a large number of cells that are inflammatory, meaning their CD16 levels are higher. They're up higher on the y-axis. They're also CD14 positive. And a third population that we see enriched in HIV disease are cells that we call patrolling monocytes. Those cells are CD16 very high and CD14 just a little dim. So we divide them on this basis into traditional, patrolling, and inflammatory monocytes. These are summary data from patients who are HIV negative in red, patients with controlled viremia in blue, and patients with uncontrolled viremia in black. And what we can see are increased numbers of inflammatory monocytes in both infected populations and increased numbers of patrolling monocytes in the untreated patients, increased numbers of inflammatory monocytes in the untreated patients, and in the untreated and the treated patients, increased numbers of patrolling monocytes. Okay. The important thing to remember about inflammatory and patrolling monocytes that are elevated in our patient populations is they're enriched for one of these homing receptors, CX3CR1, which is the fractalkine receptor, which allows them to accumulate on the endothelium that is expressing the ligand fractalkine. Patrolling and inflammatory monocytes have high levels of fractalkine receptor. These monocytes also elaborate inflammatory mediators, so if you expose them to microbial products, such as PAM3CSK4 or a lipopolysaccharide, these are bacterial products or analogs of bacterial products, you can see in these panels that we make high levels. These monocytes are capable of making high levels of inflammatory mediators, IL-8, IL-1 beta, IL-6, IL-10, which has some counter-regulatory mechanisms. And in this particular panel, there wasn't a lot of TNF made, but often it is. So let me ask you a question. If we have high levels of IL-6 that you saw on that panel, and high levels of tumor necrosis factor in the plasma of a person, where does that stuff come from? What's the source of those inflammatory mediators? Are they made by blood cells? Are they made in the tissues? Are they made in the muscles? Are they made in the lymph nodes? Are they made in the gut? The answer is nobody has a clue. In general, cytokines are made in tissues, and they act upon cells that are nearby in order to persuade one cell to get another cell to do its bidding. But that doesn't mean that that these things work at a great distance. But yet, we measure these things in plasma, uncertain as to where they come from, and have learned that high levels of these mediators are biomarkers for disease. But we can't really say that they cause disease until we can prove this in the right kind of model. Nonetheless, I've moved away from the story just a little bit, but the fact is these monocytes that we can measure in blood are capable of making these inflammatory mediators if stimulated. Okay, here's another character we need to know about, and this is a guy who's very important. This is tissue factor. Tissue factor is expressed on the surface of a variety of cell populations. In particular, it's expressed on the surface of monocytes. And what tissue factor does is it activates, it cleaves factor VII, like a zymogen, making it more activating factor VII that ultimately begins the coagulation cascade. So this is the way that the extrinsic coagulation cascade is initiated, and it can be initiated by tissue factor that's expressed on the surface of blood cells, monocytes, endothelial cells. This product, an intermediate product of the coagulation cascade, is thrombin. Remember, and you're going to be hearing about this again, thrombin is made and activated downstream of the action of tissue factor expressed on the surface of monocytes. So how do we look? We can look at tissue factor on monocytes by flow cytometry, and in the absence of stimulation, the levels of tissue factor on the monocytes of a healthy control are relatively low. But if we stimulate those cells in vitro with bacterial products, here lipopolysaccharide, a TLR4 agonist, here flagellin, a TLR5 agonist, these are both bacterial products, we can dramatically upregulate the expression of the procoagulant tissue factor on the surface of monocytes. What do monocytes look like in the blood of patients and controls? In each of these panels, we have cells from HIV negatives in red, from HIV positives with controlled viremia in blue, HIV positives with uncontrolled viremia in the black. And we can see that the proportions of cells, this is the y-axis, proportions of these monocytes expressing tissue factor is fairly low in traditional monocytes. Those are the bulk of all monocytes in uninfected individuals. Relatively higher in inflammatory monocytes, but particularly high among patients with uncontrolled or controlled viremia, and very high in patrolling monocytes among patients with controlled or uncontrolled viremia. It doesn't seem to make much of a difference. Whether you're on antiviral therapy, your inflammatory and patrolling monocytes are enriched for the expression of tissue factor. What does that mean clinically? Well, what that means clinically is in green, we have the proportion of circulating monocytes expressing the procoagulant tissue factor from patients who are experiencing an acute myocardial infarction. And so what you see is these cells are very procoagulant. These people are having a heart attack. They're having a heart attack now. Tomorrow, after therapies, those tissue factor monocytes are going to be diminished. But every day, our patients are walking around with high tissue factor expression on their patrolling and inflammatory monocytes. And this tissue factor can activate coagulation. What else can activate tissue factor, can upregulate tissue factor and change the inflammatory profiles of monocytes? Well, LPS, here are monocytes from a healthy control. If we expose those monocytes to LPS, they move upwards on CD16, so they become more inflammatory. If we do that with low-density lipoproteins, nothing happens. But if we expose these cells to oxidized low-density lipoproteins, they become more inflammatory too. So bacterial products, inflammatory lipids can upregulate inflammatory patterns, the inflammatory phenotype on monocytes. What about effects on tissue factor? Well, you saw before that LPS could increase tissue factor. Y-axis here is tissue factor. That LPS could increase tissue factor on monocytes, but so can oxidized low-density lipoprotein in both inflammatory and patrolling monocytes. Ordinary low-density lipoprotein doesn't seem to have that effect. Do we find high levels of oxidized lipids in the plasma of our patients? Well, just looking at this family, and there are better ways to look at oxidized lipids in HIV disease that I'm not going to show you today, but levels of oxidized low-density lipoprotein are elevated in HIV-positive individuals, shown here in blue, who have controlled viremia, and in black with uncontrolled viremia. And it turns out that these oxidized LDL levels correlate clinically to levels of soluble CD4 T, the LPS co-receptor, a marker of monocyte activation. They correlate clinically to tissue factor levels on patrolling monocytes, and in a broader way, oxidized LDL levels in our patients correlate with the index that we call Framingham cardiovascular risk, a predictor of risk of cardiovascular events. So I'm just going to summarize this story about monocytes in HIV infection. The numbers of inflammatory and patrolling monocytes are increased in HIV infection, and these are the published papers that show us this. These inflammatory monocytes can elaborate cytokines in response to microbial elements like LPS and flagellin, as well as to oxidized lipids such as found in oxidized low-density lipoprotein. These cells are enriched for expression of the procoagulant tissue factor that activates the coagulation cascade. They express the fractalkine receptor CX3CR1 that lets them accumulate on the surface of the blood vessels, the endothelial surface of the blood vessels, and in data that I haven't shown you but is published by a couple of groups, monocyte markers, soluble monocyte markers reflective of monocyte activation, soluble CD163 and soluble CD14, are linked to cardiovascular risk in treated HIV infection. All right, changing gears. I told you half the story. I hope I made a persuasive case that monocytes are plausible drivers of cardiovascular risk in treated and untreated HIV infection. What about the CD8 T cells? Well, let's talk a little bit about those cells. First off, CD8 T cell numbers are dramatically expanded in HIV infection. They increase early during HIV infection when people acquire HIV infection, but they persist after viral load is suppressed by antiviral therapy. The phenotype of these cells is matured, effector-type cells. In chronic infection, they often have what we call a senescent phenotype, meaning they're not capable of much replication, but they are still capable of an inflammatory cytokine response. It's important to know that despite the fact that they're expanded in chronic HIV infection, these cells in treated HIV infection are not HIV reactive. The frequency of HIV reactive cells among the CD8 population is very low. CD8 T cell activation, typically reflected in expression of CD38 and HLA-DR, predicts rapid course of disease in untreated infection. This was work by Janice Georgi's group from the 90s. And in the more modern antiviral therapy, CD8 T cell expansion, just absolute numbers and a resultant low ratio of CD4s to CD8 T cells predict morbid outcomes in treated HIV infection, and this has been shown by several groups. Okay, just to show you what the CD8 T cell counts are in patients with well-controlled viremia. These patients have been on treatment for an average of 8 years, and their CD4 T cell counts in the HIV positives in the red are about twice the CD8 T cell counts of healthy HIV uninfected controls. But there's a hooker, and this is a hooker that I'm not going to be able to explain fully, so it's something that should give you pause about everything that I'm going to say, but here's what it is. We only see CD8 expansion in HIV-infected persons who are also co-infected with cytomegalovirus. So the CD8 T cell counts in the in the CMV negative people shown here are largely similar to those seen among healthy controls, a little bit higher, but they're dramatically lower than those seen in CMV seropositives. So throughout the course of this presentation, maybe you'll ask yourself, why do we only see the CD8 expansion in people who are CMV co-infected? This is a graphic of what happens to CD8 T cell counts over time in a cohort of people who are HIV infected. Before therapy here, CD8 T cell counts go up, and despite suppressive therapy, there's a decrease, but not a significant decrease in the first year, and these numbers stay pretty much stable. A little bit of a drop over time, but not very much. These numbers stay high, as I showed you in that earlier slide. Okay, if CD8 T cell numbers are high in treated infection, why are they high? Are they continually dividing and replicating and turning over, or are they not? Well, the answer is they're not. In order for a cell to divide, it needs to go through cell cycle, and we have a way to measure cells in cell cycle, and that is by intranuclear expression of an antigen of uncertain function called Ki67. It's a marker for us. We can see it easily on a flow cytometer, but we don't really know what it does. So we looked at several different groups. We looked at healthy controls, where the frequency of Ki67 expression on CD8 T cells was about 2%. We looked at healthy old people, people as old as me and Guido, and they were also about 2%. We looked at people who had treated HIV infection, who had immunologic success. They expanded their CD4s normally, and they had the same normal cycling of CD8 T cells. And we looked at people who had immunologic failure. They too were normal. Even in people who couldn't raise their CD4 T cell counts, cycling of CD8s were normal. The only population that had high turnover, high cycling of CD8 T cells was HIV-positive, untreated individuals. And their cycling frequency was high, 8 times higher than other populations, averaging 16% in this group. Okay, so that means that the cycling population is the population that is probably playing a role in the expansion of these CD8 T cells. So what's driving it? Are they being driven by antigen, or are they being driven by bystander mechanisms? Well, we got to look at that by looking at the structures of the T cell receptors in the cycling and non-cycling population. So there are commercial antibodies, 24 antibodies in different colors that will allow you to look at the V-beta structures of T cell receptors of different T cells by flow cytometry. So we looked at Ki67 negative cells here, Ki67 positive cells here, and the same here, negative and positive here. And each of these panels represents, in this individual, this particular V-beta structure is in one color, this V-beta structure is in another color, and this V-beta structure is in 2 colors. So we can, at one time, in one particular panel, look at 3 different V-beta structures. The bottom line is that the V-beta structures of the cells in cycle very much reflect the V-beta T cell receptor structure of the cells not in cycle. And we could confirm this when we did a Spearman correlation. And in this instance, we looked at the data from all of our patients, 10 patients, 10 healthy controls, and we found that the cycling cells were correlated beautifully with a Spearman correlation of about 0.9 or better with the V-beta expression on the non-cycling cells. So using this very gross estimate of T cell receptor diversity, it looked as though the cells that were cycling had largely the same T cell receptor structures as the cells that were not cycling. However, this is not it's not a very sensitive readout of T cell receptor diversity. So we went after it in another way and did the sequencing of the CDR3 regions of the T cell receptor among cells that we sorted that were in cycle versus same effector memory cells that were not in cycle. And on the y-axis, we have the percentage of each dot. Each dot represents a particular T cell receptor sequence. The y-axis represents its proportionality of all the effector memory CD8 cells that were not in cycle, and the x-axis represents its proportional representation among the cycling cells. So these, in this instance, this is 0.01%, 0.1%, 1%, and 10%. And what you can see is that the proportionality of each of these different clones, each of these dots represents a different clonal sequence, is the same in the resting population as in the cycling population. This is one particular patient. When we look at 3 patients and 3 controls, you can see that the proportionality is the same. So the data we have so far suggests that cycling in untreated HIV infection is performed largely by cells that are reflective of the T-cell receptor diversity of the entire population of effector memory cells. And we can analyze that by doing a Shannon entropy calculation. The CD71 negative cells are non-cycling. The CD71 positive cells are cycling. That's actually how we distinguish between those, because it's a surface marker that lets us pull out the DNA of these cells. And the Shannon entropy coefficients were the same for all these populations in controls C and in viremic patients V. All right, so it looks like it's a bystander mechanism. But then how do we reconcile that with the CMV data? All right. When we look at the frequency of cycling according to antigen specificity, we have to start looking at some antigen specificities to get a better handle on this. When we look at the T-cell receptor diversity at the cycling of cells with different antigenic specificities, we find that cells that react with influenza peptides or CMV peptides in healthy controls don't seem to be cycling any more than the general CD8 T cell population. These are no more, probably even less. When we do the same experiment in an HIV positive person, we find something entirely different. We find that the cycling of CD8 T cells, first, it's much higher. These y-axes are different. Here we're again at about 16%. Here we're at 3%. So these guys are cycling much higher, but even higher is the cycling among cells that are reactive with influenza peptides, with cytomegalovirus peptides, and with HIV peptides. We sort of expected this with CMV and HIV because these guys are constantly making antigen, and there's constant exposure to viral antigen. But for influenza, half of these guys, I don't know that any of them had influenza. Some of them might, but none of them were sick when we studied them. And half of these guys were studied in the non-influenza season, so they hadn't even seen influenza vaccine. So somehow, cycling is increased among cells with some memory for viral peptides in HIV disease. Let's look at a little more detailed look at the phenotype of CD8 T cells in people with HIV disease. So on the bottom panel, we have HIV-infected individual. On the top, we have a healthy control. And here we're looking on the y-axis, we have reactivity with tetramers containing peptides from HIV. Of course, the control has none. And on the x-axis, we have the frequency of granzyme B expression. Granzyme B is a critical element on the cytolytic pathway. Granzyme B is the character that the cytolytic T cell injects into the target cell in order to start disrupting the cell and initiating the cascade of programmed cell death. First off, you can see that there's much more Cas-based granzyme B expression in the CD8 T cell population of the HIV-infected persons than among the controls. Proportionally, there's usually 2 to 3 times as much. When we look at the controls and we look at the granzyme B expression by cells that react with influenza or CMV, it's sort of a little higher than we see in the general CD8 population. But look at the HIV-positive patients. All the peptide tetramer reactive cells are granzyme B positive. So there's this bias towards increased expression of the cytolytic molecule granzyme B by effector memory CD8s in people with HIV disease, and it's particularly so among cells that have remembered viral peptides. Okay, I'm missing a slide. Yeah, all right, no, I'm not, we're good. So how do we reconcile this? How do we reconcile this story that we see what looks to be bystander-like expansion and cycling of CD8 T cells in HIV disease, and that the cells that seem to be cycling have a memory for viral peptides and have a cytolytic capability particularly enriched among cells with memory for viral peptides. Well, so we exposed cells from healthy controls to a variety of cytokines that we knew could or did result in T-cell expansion. And the cytokines we chose were IL-2, IL-7, and IL-15, each common gamma chain receptor cytokines that we know can drive T-cell expansion. And we additionally looked at IL-6 and IL-1 beta because of some previously published work that we had that could show that those inflammatory cytokines could drive T-cell proliferation. And the bottom line is, the phenotype that we get is that interleukin-15 is particularly good at driving T-cells into cycle. We see that here. This is the IL-15 panel. And especially good at driving cells into cycle that have peptide tetramer reactivities. Here, influenza and cytomegalovirus. These are from a healthy control. So IL-15 sort of mimics in vitro the phenotype that we see in HIV disease by driving cells into cycle, particularly so among cells with memory for viral peptides. What about granzyme B? The same thing. Of all these cytokines, IL-15 can upregulate the expression of granzyme B, particularly so among cells with real memory for having seen viral peptides. So we looked at the IL-15 in the nodes of our patients, healthy control, HIV positive untreated, HIV positive on ART, and we can see that IL-15 levels in the nodes are very high in patients who are untreated, and these are the summary data, healthy controls, untreated, and with therapy, IL-15 levels in the nodes come down to normal levels, and there's a very nice correlation between lymph node levels of interleukin-15 and circulating CD8 T cell count. So the story we're going to try to tell you is that in HIV disease untreated, a cytolytic cycling phenotype is induced by exposure to the homeostatic cytokine interleukin-15 that's expressed at high levels in the lymphoid tissue. All right, now what do these CD8 T cells do? What are they actually doing in people with HIV disease? We know that they correlate with the risk of atherosclerotic plaque, and we can actually find them in people who are not infected. We can find activated CD8 T cells inside atherosclerotic plaque. The CD8 T cells in HIV disease have high expression of that very same fractalkine receptor that monocytes have that allow them to accumulate on the endovascular endothelium. Importantly, the cells that are fractalkine receptor positive, right here, in treated HIV infection, have high expression of another important receptor called protease-activated receptor 1, as 80% of the fractalkine receptor positive cells from patients with HIV disease, these are CD8 T cells that are capable of homing to the vascular endothelium, express PAR1. Why do we care? Well, it turns out that PAR1 is cleaved and activated by thrombin, that is the procoagulant that is in the pathway that's initiated by monocytes expressing tissue factor. Monocytes have tissue factor, they activate factor VII, the coagulation cascade goes down, thrombin is in that cascade, thrombin activates PAR1 that's expressed on these CD8 T cells. So, here's the model. This is a blood vessel. This is a blood vessel, this is the endothelium. Crawling around this endothelium are monocytes that express fractalkine receptor that get them to stay there. Likewise, crawling nearby are these CD8 expanded cytolytic CD8 T cells expressing fractalkine receptor. Other things circulating around that include, in untreated infection, HIV, in treated and untreated infection, oxidized lipids, in treated and untreated infection, bacterial lipopolysaccharide, all activate monocytes to express tissue factor that activates the coagulation cascade by cleaving factor VII, resulting in the formation of thrombin that acts on PAR1 on a nearby CD8 T cell to activate this monocyte, this CD8 T cell, to be cytolytic, to damage the endothelium, and to make it easier for CD8 T cells, monocytes, and other inflammatory cells to migrate through the endothelium and form a clot. I think that's a great story. My mother thinks it's a great story. I'm not sure that study sections think it's a great story yet. But it turns out that rhesus macaques also think it's a great story. This is the aorta of a non-human primates that have been infected with SIV or SHIV. And what you can see in the SHIV-infected animal here are CD8 T cells. First off, you can see inflammatory cells on the vascular endothelium of the SHIV-infected, but not the SHIV uninfected animals. And in the SHIV infected animals, we can see CD8 T cells, CD68 monocytes in close proximity. And here are the summary data on the CD8 cells in the SHIV infected animals and the uninfected, and the monocytes in the SHIV infected animals and the uninfected. So there are more monocytes and there are more CD8 T cells on the endothelium in SHIV infected animals than in the controls. What does this do to the endothelium? Well, it's not good. First off, in the SHIV-infected animals, it downregulates the expression of Kruppel-like factor II, which is a potent anti-inflammatory mediator, transcriptional mediator, in the endothelium of these animals. These are the SIV and SHIV-positive animals. These are the controls. So an anti-inflammatory regulator is decreased, promoting inflammation. What's the consequence of that? Well, we need endogenous nitric oxide synthase in order to relax our blood vessels so that we don't get vascular turbulence and stiffness. And eNOS levels are decreased as a result of this inflammation. These are the SHIV and SIV positive animals. These are the healthy controls. So that's the story I'd like to tell you. And here's the summary. People with treated infection are at risk for cardiovascular morbidities of aging, and these are predicted by coagulation and inflammatory mediators. Monocyte subsets are inflammatory and procoagulant, and this can be driven by microbial products translocated from the gut, by inflammatory lipids, and although I didn't show you this, we published it, it can be done by HIV itself. Mature CD8 T cell numbers are increased in HIV infection. They can home to endovascular sites, and we know that epidemiologically they're linked to ART-era cardiovascular morbidities. CD8 T cell expansion is also linked to CMV co-infection. That's clear, and it may be driven by exposure to the homeostatic cytokine interleukin-15 that also makes CD8 T cells more cytolytic. Inflammatory blood vessels, inflammatory cells will accumulate on the blood vessel walls in SIV and SHIV infection, and this is linked to endothelial and vascular dysfunction. And my summary is how I started, and that is coagulation and inflammation collaborate to drive increased cardiovascular disease risk in treated and in untreated HIV infection. These are the people who did the work. A lot of the CD8 T cell work was done by Mike Freeman and Suhail Yunus. Nick Funderburg did the monocyte work, and he's now on faculty at Ohio State. And these are my other collaborators at Case. People at other places. Jake did a lot of the really beautiful immunohistochemistry. And this is the NuWorks Concept Sheet 329 team that generated the data that I showed you in the first slide. Do I have 2 minutes to talk about something else? 2 minutes? I think I'm good in terms of time. Here's what they are. I want to tell you about a new journal that we just started, and this journal is designed to make your life better. I know that we've all struggled with biomedical publications, and everything is a struggle and is difficult. This journal was just launched a few weeks ago. We got a great review in Science by John Cohen. He loves the idea, and let me tell you about the things that make this good for all researchers. This journal was designed by researchers for researchers. It only takes 5 minutes to submit an article on our journal. Usually takes half a day or more. We will accept for review papers to review in any National Library of Medicine approved format, so that you don't have to reformat your paper just to send it to us for review. We will ask you to revise it if it's accepted, but the submission can be in any format. If you want, if you've had a good review from another journal, but they couldn't take it for priority, you can send us that review and your response to that review, we probably won't even send it out. Our editors will make an editorial decision, so it'll be rapid. There are no fees, at least for the first couple of years, and one of the reasons that we do this well and quickly is that we pay our reviewers. Our reviewers actually get paid to give us timely reviews. So, if you've got a good paper, you want to send it to a really interesting journal that's going to launch. Our first issue will probably be in August. Send it to Pathogens and Immunity, and I'll be glad to take any questions now. Thank you.